My name is Ahmed Kovacevic. I'm the director of the Center for Compressor Technology at City St. George's, University of London. Our center specializes in fundamental and applied research, knowledge transfer, consultancies, design and delivery of tailored services on positive displacement compression and expansion machines. Welcome to this week's Lecture Tuesday. Screw compressors are used to compress a variety of gases in different industrial applications, including industrial air compression, refrigeration and air conditioning, heat pumps, petrochemical and gas industries, as well as in the food, beverage and pharmaceutical industries. Almost 20% of electrical energy produced worldwide is used for compression. Reducing energy consumption of compressors is one of the major tasks for achieving net zero economy. Therefore, screw compressors should have good performance both at full and part load. In this short lecture, I will talk about efficiency of three most used capacity control methods of rotary positive displacement compressors, including screw compressors, and how capacity control methods influence their performance. Performance of compressor can be conveniently defined through a specific power, which can be expressed as a power over the unit of volume flow or power over the unit of mass flow. The latter one will be used in this lecture. How can compressor capacity be regulated? To understand that, let us review basic definition of the volume and mass flow. Volume flow rate is, in equation 1, is defined as the difference between the displacement Vt at certain speed n and the leakage losses Vl. To obtain the mass flow rate in equation 2, the volume flow rate is multiplied by density of the gas at suction. By substituting density with this equation of a pressure over ZRT, one can obtain equation 4. Parameters in this equation 4 define how capacity can be regulated, and this is by changing the suction volume, changing the compressor speed, changing the suction pressure, or by changing the suction temperature or gas composition. The first three are practically possible and used, while the last one is impractical. Let us now examine how each of these modes of capacity control are practically implemented and how can they affect performance of a compressor. Effects of different capacity control methods will be shown on this typical oil-injected air screw compressor installed at City University of London. It has an end rotor profile with a lobe combination of 4-5, size of 140 millimeters, L/D ratio of 1.55. Its displacement is 2.11 liters per revolution. It compresses gas from 1 to 8.5 bar, has volume index of 4.6, can operate between 1500 and 5500 RPM, and the nominal speed is 5,500 RPM. The most common method to control compressor capacity in process gas and refrigeration is by a sliding valve shown in the clip. The same effect can be achieved in a stepwise manner by individual puppet valves shown in the image on the right. As the slide valve moves away from the slide stop, it allows the suction gas to recirculate without a large penalty in power consumption, until the gas is completely trapped by the rotors at the actual position of the slide valve. This delays the start of compression by reducing the volume trapped within the compressor, as shown by successive red lines in this diagram. Moving the slide valve from the original position defined as at angle 0 when the suction volume is maximum to its ultimate opening position defined by the angle of 250 degrees will reduce capacity of this compressor from 12 to about 3 kilograms per minute. The minimum capacity is then about 25% of the maximum capacity of this compressor at a constant speed of 5,500 RPM. As shown in the bottom right diagram, the specific power will increase from 5 kg per minute at maximum capacity to around 9 kilowatts per kilogram a minute at minimum capacity. Although relatively efficient, a slide valve can significantly increase complexity and cost of a screw compressor, and therefore it is commonly used only for large screw compressors. The most efficient capacity control method is by speed variation. Variable frequency drives with permanent magnet motors are used for this purpose and are common today, while their cost is constantly reducing. This method is used for medium-sized compressors, industrial refrigeration, heat pumps, and air compression. The figure shows directly driven variable speed oil-injected air screw compressor. Compressor systems with VFD drive are simple and allow flow reduction directly proportional to rotational speed. In our example, the flow rate is reduced from 12 kilograms per minute to about 3 kilograms per minute by reducing compressor speed from 5.5 to 1,500 RPM. Due to its relatively flat characteristics and a wide range of operating speeds, the specific power is not much changed by reducing the flow. At only 20% capacity, the specific power is increased by only 20% from 5 to 6 kilowatts per kilogram and minute. This is by far the most efficient way of controlling capacity of a screw compressor. Throttling is the cheapest control capacity method, as it only requires a simple butterfly valve, which is a common element in any compressor system. By reducing the suction pressure, the mass flow rate is linearly reduced, but at the cost of significant increase in specific power, as shown in the bottom diagram. The specific power at 20% capacity has increased for 5 times compared with the nominal specific power at maximum capacity. Despite that, the total power consumption at the minimum flow is small, and therefore this is still a viable method to control capacity of smaller industrial and domestic air compressors. Let's summarize. The most efficient capacity control is by variable speed, represented by the black curve in the diagram. The downside is that such systems require variable frequency drive and appropriate motor, which could be expensive. Capacity control by a slide valve, represented by a blue line, requires more complex design of a screw compressor and is less efficient than a speed control. However, this is a preferred method for large compressor systems where the cost of VFD is prohibitively high. Throttling, shown by the orange line, is the cheapest way to control capacity, but operational costs at a part load are up to 5 times higher than for variable speed control. Despite that, this is often used for small air screw compressor systems. With that, we conclude today's short lecture. For any future discussion and questions, please get in touch by email and visit our website for more information about the Center for Compressor Technology at City St. George's, University of London.